Section 14.3 covers partial derivatives. So we want to understand what the definition and the meaning of a partial derivative is, and then to compute the first and second partial derivatives and apply Clairaut's theorem to see that in what cases mixed order partials are going to be equal to each other. So let's have a look at that. We're going to start with how we can think about taking the derivative of a function with two variables. So if I have a function that has two variables, let's see if we can think about the graph of that. I know that if it has two variables, then its graph is going to live in three-dimensional space. So what I can think about is, right, that derivative should tell me a slope, but now I don't need to know sort of which direction I want to go in. So I can think about moving in the direction where x is constant, and I get a nice curve in space. And if I have that nice curve in space, then I could take the derivative of that curve in space where x is constant. So what I want to think about is treating my different variables as constants and then taking the derivative of that function that's left. So let's go ahead and write some details down about that. So what we're going to do is we're going to treat one variable as a constant and take the derivative with respect to, right, so I'm going to use that abbreviation WRT, with respect to the other. Okay, so what's this going to look like? If I have f sub x, that means the partial derivative of f with respect to x. So because I'm taking the derivative with respect to x, that means I'm going to treat y, the other variable, as a constant. Okay, so what does that mean? Let's say I have f of xy equals 2xy plus 3x squared plus y. So what I'm going to think about, if you're having trouble with this, you can kind of do this in your head or even do it out on your paper. I'm going to think of the y as something like a constant. So maybe I'm thinking of it as a 4. So if I had this function that only depended on x, and it looked like 2 times x times 4 plus 3 times x squared plus 4, I want to think about what the derivative would be. Right, well, if I have this derivative, this is just a constant times x, so I just get the constant, and let me actually just write that as 2 times 4, plus I take the derivative of this term with respect to x, I get 6x, and then that's plus 0, because the derivative of 4 is just 0. Right, but this 4 here is really just playing the role of my y. So if I take the partial derivative of this function with respect to x, the 2 and the y are my constants, so that's the derivative of 2y times x. I just take the derivative of this with respect to x, I get 6x, and then the derivative of y with respect to x is just 0. So I'm getting that 2y plus 6x. Right, so that's my partial derivative of f with respect to x. I could also do f sub y, and that's going to be the partial derivative of f with respect to y, and in that case I'm going to treat x as a constant. So in this case, my f of x sub y, again equaling 2xy plus 3x squared plus y. The partial with respect to y, well, that 2x is just a constant times y, so that's what I get when I take the derivative of just y. Now 3x squared, this whole thing is a constant with respect to y, so that just becomes a 0 when I take the derivative, and the derivative of y with respect to y is just 1. So I just get that 2x plus 1. This takes a while to get used to, this process, so we'll do a bunch of examples in just a little bit. But for right now, the thing that you really need to have in your mind is that when you take the partial with respect to x, your y is a constant. When you take the partial with respect to y, your x is a constant. Let's talk a little bit about this algebraic definition. So when I'm talking about my partial derivative of f with respect to x, right, this is the one where we're treating y as a constant. What I'm going to do is I'm going to have a limit definition just like we did in Calc 1. So I have the limit as h goes to 0. I move my x by a little bit, so I change that x, but I keep y the same because I'm keeping it as a constant. So if I evaluated this limit where the y just stayed a y, but the x made that small change, that would give me that partial with respect to x. If instead I want to do the partial with respect to y, then I just need to treat that x as a constant. So in my limit definition, the x stays the same, and then the y changes by a little bit, and then we should have that h on the bottom still. Okay, so what does this look like? There's some different ways that I can write this. So if I want to be really explicit that my f of x is a function of x and y, I could write my partial with respect to x, or f sub x of x and y. If we don't need to be as explicit that it's a function, we could just call it f sub x. And we can also use the d notation. So because it's a partial derivative, I use a fancy partial d, it's called. So it's like a fancy script d instead of a straight up and down d. So when we're talking about partial derivatives, we use this curly d. And so these are all of the different ways I could write this. So the partial derivative with respect to f with respect to x, or d by dx of f of xy. And sometimes it's even called partial. So I could call this partial d by dx of f of xy. You might also see this as if you have z equals your function of x and y, you could also call this dz dx, or partial z dx. We have similar conventions for y, right? So partial with respect to y of x and y is the same as f sub y, which is partial df dx, or d by dx, or partial d by dx of x and y. Oops, they should be y's, not x's. Let's fix that. So I get all of these same notations if I'm doing a partial with respect to y. So geometrically, what are we actually finding? If you remember, we had this demo where we looked at the different traces, the x traces and the y traces. And those are just the curves you get where x is equal to a constant and y is equal to a constant. So when I'm doing a partial derivative, what I'm actually doing is I'm taking my function, I'm setting y equal to a constant, so maybe this is y equals to 3, and I'm looking at the curve I get, that single variable curve in space, when y is equal to 3. And now, given a point on that curve, because I just have a single variable curve, I can think about the slope of that tangent line. So what my partial derivative is giving me is it's telling me the slope of the tangent line of that curve when I restrict my function. Right? So this is where y is a constant. So since y is a constant, that means I'm looking at the change in x. So I'm looking at my partial derivative of f when I'm changing my x. Right? X is changing, but y is changing the same. And if I look at my slope here at this specific point A, so it's kind of hard to see, but there was a specific point A that was noted here. If I'm moving in that x direction, the function is going up. I get that positive slope, which means my f sub x should be positive since the z is increasing when we move in the positive x direction with y constant. Okay. Now I can do the same thing if I look in the other direction. So if I let x be some constant here, when x is constant, we get a different curve. So then that means I can let my y changes, or let my y change. So I'm looking at the function change as y changes. And now for this same point here, As y changes, my function is decreasing. So here my f sub xy is negative, since as y changes, the function value decreases. So these partial derivatives allow me to describe the increasing and decreasing behavior as I move either in the x direction or in the y direction. We just have to be careful, right? When x is constant, that's the partial with respect to y, and when y is constant, that's the partial with respect to x. If you want to see a three-dimensional demo of this, you can go and check out this GeoGebra demo at this web address. Kind of play around with it some. Now that we've seen the algebraic and geometric interpretation of these, let's go ahead and just do some examples. So in each of these, I want to find the partial with respect to x and the partial with respect to y. As you're going through and working through this video, I encourage you to pause it, go ahead, try these on your own, maybe one or two at a time, and then come back, watch the video, and see if you got the same thing that I got, as a way to kind of check your understanding as you go. So for the first one here, if I do the partial with respect to x, I want to think of y as a constant. So the derivative of 3x with respect to x is just 3. And now I'm just subtracting away a constant here. So that's derivative of a constant is just 0. So that's the same as just 3. And then my partial with respect to y, thinking of x as a constant. So 3 times x is a constant, its derivative is just 0. And the partial with respect to y is just negative 5. For the next one, I'm going to do partial with respect to x. Now again, my y is just a constant. So whenever you have a constant times by your function, and you take the derivative, that constant just comes along. And then you just take the derivative of what's left. So I'm going to get 3 halves x to the 1 half times y to the negative 2. So if I wanted, I could simplify this down to 3 root x over 2y squared. But we don't have to do that. For the next one, partial with respect to y, now x is a constant, so this x to the 3 halves is just a constant, which is multiplied by my function. So it's going to come along when I take the derivative. And then I take the derivative of y to the negative 2, which is y to the negative 2, negative 2 times y to the negative 2 minus 1, which is negative 3. So again, if I wanted to simplify this down, I could have negative 2x cubed square rooted all over y cubed, or we can just leave it the way it was. All right, it's getting a little more complicated as we go. For this one here, let's do the partial with respect to x. Y is again a constant, so 5y squared is just a constant that comes along. I take the derivative of x cubed, which is 3x squared, minus derivative of x with respect to x is just 1, plus, this is just a constant with respect to x, so its derivative is 0, minus ln of y is a constant with respect to x, and then I have to take the derivative of 3 times x to the 1/3, so 1/3 times 3 is just 1, x to the negative 2/3. So I can simplify that down a little bit to get 15 x squared y squared minus 1 minus ln of y times x to the negative 2/3. Okay, so for my partial with respect to y, now I want to think of x as a constant. So 5x cubed is all a constant here. Derivative of y squared is 2y. Minus x is a constant, so its derivative is 0. Plus the derivative of e to the 2y is 2e to the 2y. Minus x is a constant, so this 3x to the 1/3 comes along. And the derivative of ln of y is 1 over the absolute value of y. Yeah, just kidding. We don't need absolute values there because the domain is positive. So I could just do 1 over y. Which again, if I want, I can simplify 10x cubed y plus 2e to the 2y minus 3 root x over y. That's my partial with respect to y. Sorry, I think my powers changed here from a 1/3 to a 1/2. So let's go ahead and just fix that. 1/3, 1/3. All right, we've got a few more complicated examples on this slide, so let's go through and do them. So for the first one, I'm going to take my partial with respect to x. So I need a chain rule, so I've got 5 times, leave the inside the way it is, to the 4th times the derivative of what's inside. I'm taking the derivative with respect to x, so the derivative of x times y is y, plus x squared is just 2x, minus the derivative of 3xy squared is just 3y squared. So that's going to be the derivative with respect to x. If I go with respect to y, again I have to use the chain rule, so we get the same starting thing. And now I multiply by the derivative of what's inside with respect to y. So x times y, x is just a constant, it comes along, derivative of y is 1. X squared is a constant with respect to y, so that one's 0 when I take the derivative. And then if I take the derivative of 3xy squared, I get minus 6xy. Because the derivative of y squared is that 2y, and I'm multiplying it by the 3x. All right, last but not least, we have a quotient here, so we're going to have to use the quotient rule. So for the partial with respect to x, I'm going to get low d high, the derivative of x with respect to x is just 1, minus high x d low, derivative of x plus y with respect to x is just 1, all over the bottom squared. So on the top I have x plus y minus x, so I end up with y over x plus y quantity squared. For the partial with respect to y, same thing, low d high, but now the derivative of x with respect to y is 0, because x is a constant with respect to y, minus high d low, 1, all over the denominator squared, so I end up with negative x over x plus y quantity squared. So again, these just take some practice. Go through, try some of these, make sure you have this process down. In this question, we're given the level curves of a function. So we're given those places where the function has a constant value, and each of those are labeled with whatever the value is at that point. And we want to know the sign of fx and fy at that green dot. So let's think about how we can do this. I'm focusing on this green dot here. When I move this direction, my x value is changing, but my y is constant. So I'm moving this direction here from that axis. And when I'm moving this direction, my y is changing, but my x is constant. So let's go ahead and move in the direction of that x-axis from the point. So here my y is constant. And I notice that my function values go from 10 to 12. So when x changes, but y is constant, we'll write that down here. X changes, y is constant, and the function is going from 10 to 12. So the function is increasing. Right, so y is constant, x is changing, y is constant, x is changing. So that tells me that I'm thinking about my partial derivative of f with respect to x. I get the function is getting bigger, it's increasing, so that's going to be greater than 0, or positive. Now let's go the other way. If I think about moving from this green dot and going straight up, if I do that, my x is constant, my y is changing. So I'm thinking about the partial derivative of f with respect to y, and my function values are going from 10 to this next line, which is 8. So they're decreasing. If the function is decreasing, that derivative should be less than 0. So my fy is less than 0 here, but my fx is greater than 0. Now that we have this idea of partial differentiation, we can extend that to this Calc 1 idea of implicit differentiation. So I've got this function z, and it's implicitly defined by x and y. So once you have an x and y, there's going to be some z value that satisfies this equation, possibly more than one. And I can take that derivative, that partial derivative of z with respect to x, but because the z is sort of mixed in with the x's and y's, I need to do this implicitly. So I'm going to treat the z as an implicit function, which means I'm going to take, when I take the derivative of it, so when we take the derivative of it, we're going to write dz dx or dz with dy, depending on which one I'm taking the derivative with respect to. And I'm still going to treat my y here as a constant. So it's a little weird because I need to do this all within the same problem. So let's see what that's going to look like. So I'm going to start off, I take the derivative of z, I'm treating it as an implicit function, so I'm just going to write that as dz dx because I'm taking the derivative with respect to x, plus the derivative of e to some power is e to that power times the derivative with respect to x of that power, y squared z. And then I keep the equal sign in there. The derivative of x times z. I have a product here. So I have x times the derivative with respect to x of z plus the derivative of x is 1 times that z, plus here I'm treating y as a constant, so that y to the 1/2 comes along, and I just take the derivative of x squared, which is 2x. So simplifying that down, I get dz dx plus e to the y squared z times, here y squared is just a constant, so I just need to take the derivative with respect to x of that z term. And that's going to equal x. We don't know what z is, so we write its derivative as dz dx plus z plus 2x root y. Now, if I wanted to, I could solve for my dx dz. So I'm going to get all of my dx dz terms on one side, and I'll factor out that dx dz. Oops, wrote the wrong thing here. So I'm factoring that out. So e to the y squared z, move that y squared up front, subtract the x over. That equals z plus 2x root y. And then I can just divide both sides by that function that's multiplied by the dz dx. So I get z plus 2x root y over 1 plus x squared. Sorry, 1 plus y squared e to the y squared z. That z there should be upstairs in the exponent minus that x. So it's a really ugly expression, right? But we're able to use implicit differentiation to help us find that. Once we take the partial derivative of a function, we get back a new function. So then I can take the derivative of that function too. All right, we don't have to stop at just one derivative. So let's kind of see what that looks like. So if I start with my f of x and y, I can take the partial with respect to x. So I get 6x plus 2y. Y cubed is a constant with respect to x. That goes away. Or I can take the partial with respect to y. If I do that, I get 2x plus 3y squared. And now for each of these, I can take more derivatives. So for this guy, I can take the partial with respect to x. So that just gives me 6. Now I can write that as the partial with respect to x, take its partial with respect to x. So I can write that as fxx. Or I can write that as partial squared f dx squared. So what we're thinking about for this notation here, it's like I have, a d by dx, and then another d by dx, and that's going for the f. So it's really like having the d squared f, and then on the bottom here, I have like a dx squared. But the way that we usually write that is without those parentheses on the bottom. But that's how I like to think about it. Okay, notation-wise, right, we can also take the partial with respect to y. So I'd write that as fx. That's what we're starting with. We're taking its partial with respect to y. So that gives me 2. So if I write fxy, that means x first and then y. But what's a little weird, right, is if I start with my f and I do x first and then I do y, the order of those would have the x closest to the f and then the y. So the y is written first left to right, and then the x. So these two notations look like they have the x and the y in opposite orders of each other, but they're actually the same. So that means x first and then y. So I get both of those. We could also have done y first and then x. So if I do y first and then x, I also get 2. Right? So that's that f y x, or d squared f dx dy, because the first thing that goes onto the f is the y and then the x. And finally, we could take the partial with respect to y, take its partial with respect to y, and get 6y. So I think one of the things that's kind of confusing here is these two different notations. It's sometimes hard to remember which one means do x first and which one means do y first. In this case, they both equal 2, so that's really helpful. It doesn't actually matter if I mess that up. And what we hope would be true is that it doesn't actually ever matter. You could do x first and then y first and then x, and you would get the same value. And it turns out true. So that fact is called Clairaut's theorem. And it has a little bit of assumptions here. So you have to assume that all first and second order partial derivatives are continuous. But as long as all of those partial derivatives are continuous, you get that the partial with respect to first x and then y is equal to the partial with respect to y and then x. So you'll see a worksheet question that asks you to verify this. And all that means is you first have to find the partial with respect to x and then with respect to y, or find the partial with respect to y first, and then the partial with respect to x of that. And then we want to show that these two things are equal. So let's go ahead and do that. I'll label my diagram here. So if I do that partial with respect to x, I get 6xy plus 2e to the x times y times the derivative of x times y is just y. And then I take the derivative of that with respect to y. So I get 6x plus, here I have a product with respect to y. So I have to use the product rule. So the first times the derivative of y is just 1. Plus the derivative of that first, that's 2exy. I'm taking the derivative with respect to y, so now I have to take the derivative of this, x times y, with respect to y, so that gives me x, and then we had that y there. So we end up with 6x plus 2e to the xy times 1 plus xy as the fxy. And now on the other side, we can first take the partial with respect to y. So we get 3x squared plus 2exy partial with respect to y. So that gives me an x. Now I take the partial of that with respect to x. So I get 6x plus, here I have a product with respect to x. So I take the derivative, the first, times the derivative of the second, plus the derivative of that first, taking the derivative with respect to x here. So the derivative of x times y with respect to x is just y, and then I have that x left over. So again, I get 6x plus 2e to the xy times 1 plus x times y. So we verified Clairaut's theorem in this specific case. We've shown that these are equal, which is what we wanted to do.